Okay, let's get started. Welcome, everyone. Thank you for being here at one of the last talks of this amazing conference, third day. So you're the resilient people, right? So much information, and you're still here to learn more. I admire that. So my name is Laila Bougria. I work for a company called Particular Software, where we build N-Service Bus and a platform around that is supposed to help you in building distributed systems, specifically message-based ones. So before I worked there, I was already out in the field building message-based systems myself. And one of the things that stood out to me is how hard it becomes to sort of debug these systems with messages flow around the system and all of that. And so this session is a bit inspired by all of that pain I have seen teams go through when they adopt messaging, including myself, right? So with that being said, I'd like to start off today's session with a story. So once upon a time, there was a retail business that decided to build a sort of online shop for their offering. And they started small, but they were pretty successful. So as this business venture grew, they quickly understood that in order to keep up with all of the changing requirements and all of that increasing complexity, that they had to start decoupling the system into sort of separate components that could evolve a bit more independently, and even by different teams. So slowly but surely, that sort of evolved into what we nowadays call a distributed system with multiple components interacting with each other. And before you knew it, we had 3 teams in the house: Team Lorem, Ipsum, and Dolor. Or the way I would say it, Dolor, with my Spanish roots. So for those of you who don't know, Dolor means pain because there's always sort of one team that takes a hit and is doing like the really, really difficult job, right? So as a way to sort of communicate between these components that are now part of this distributed system, they chose to use messaging. So let's take a look at one of the sort of most crucial business processes that is a part of this system: placing an order. And we sort of know how this works, but let's go over it anyway. So we want to store the order in some database. We also want to make sure that we charge the credit card so we can actually make some money. And then we want to package the order, ship it, and then also make sure that we include an invoice for the customer so they have some proof of their purchase. And then we also may want to adjust the stock based on that purchase that was just completed, and also figure out whether we want to maybe order some more stock to see, is this product now almost depleted and do we need to back order it, for example. And then finally, we also want to verify the customer status to see, was this their first order? Then maybe they get a discount code because that's how we can pull them back in. Or maybe if it was their 100th order, then they're now a gold customer or something like that. So if we think in terms of these responsibilities, in terms of the sort of teams that we're managing them, we have Team Lorem sort of responsible for the order fulfillment part. We have Team Ipsum responsible for everything regarding the stock, and Team Dolor responsible for everything regarding customer care. Hence the name, right? So if we think in terms of the messages that are flowing through the system to sort of support this business process, then we could come up with something like this. So we have a sales component, a payments component, and a stock component, and they all have sort of their own commands and events that sort of support this business process from beginning to end. But looking at the system this way doesn't really tell us anything, because it hides the entire complexity about how are these components sort of interacting with each other, and who's sending a message to who, or maybe which components are reacting to which event and how is that evolving. So in order to get a better understanding of that, we always need to sort of draw the system in terms of interactions, which gives us a completely different picture, right? Everything starts in sales, make sure that payments gets that payment done, and from there on, we'll publish an order placed event that is then sort of subscribed to by multiple other components in the system, and they just do whatever is relevant to that specific component that they're in, right? The publish-subscribe pattern. And one of the advantages of doing things this way is that we end up with sort of autonomous components that are just reacting to sort of events that are occurring in the system, and then doing whatever action makes sense within that business component. So that leads us to those autonomous components, and that brings us many advantages. One of them is that it sort of allows our teams to operate in a sort of autonomous manner. What does that mean? Well, it means that they can evolve that component, following their own planning and their own requirements, but it also means that they can choose whatever programming languages, frameworks, and tools that best suit their needs, right? That could be different. It also means that each of those components can operate in isolation. So given that we're also using messaging in the system, it means that if one component is down, normally the rest of the system should be able to continue operating without too much friction. And as long as the interactions between these components are based on a set contract, which in our case is messaging, right? They should be able to evolve independently as well. Now, the thing is that anything that can evolve independently can also fail independently. So let's take a look at one of the exceptions that our team Ipsum ran into. So it's showing a pretty simple stack trace. We're trying to process an update product stock message, and we're running into an exception because we cannot find the product that is specified in that message input. So when the engineers on Team Ipsum look at this, they immediately start racing through a bunch of questions, right? So they think about what happened. You know, where did it happen? In which context did it happen, and why? Usually we'll look at the exception message, maybe see if there's any inner exceptions, look at the stack trace to sort of try to understand what happened here. And normally debugging is then the next step, right? Because that's how we sort of build up like a step-by-step context of how data is flowing through the system, what are we changing, what are we passing on, so that we can sort of understand what is the root cause of this failure. Now, the thing is that if you're running in a message-based system, you're going to have to ask yourself a bunch more questions to be able to understand what's going on. First of all, you need to understand which specific action started the specific chain of messages that we are seeing at this point. You also need to have a thorough understanding of which components are basically involved in that sort of business transaction that we are executing here. We also need to understand which specific sequence of messages that are being sent, because that might also be different. And finally, in which specific order they are being executed and how that may have an impact on the sort of behavior that we're perceiving in the system. So let me take a moment and step into the shoes of the engineer that's assigned this issue, this stack trace that we just looked at. And you can decide for yourself if I'm speaking from experience, okay? So I look at the exception message, and I'm like, product not found. Okay, looks simple enough. Let me just quickly debug this. So I look at that failing message, drag it back from the error queue to the input queue, start that component, and boom, immediately I run into the exception. So I start looking at the state that I have available, the exception message, all of that. And then I think, okay, let me just take a look at the call stack to see how I got here. The thing is that I scroll down only to understand that I'm ingesting a message off a queue. So that's not giving me much insight. I don't know how I got here. Well, that's no problem. I'll just start the initiating component that started this entire business transaction, and I'll just take it from there, and then I'll be able to, step into the next method, F10, F11, debug through it. But that's not going to work either, because at some point, we are either sending a command or publishing an event, and that's being handled by another component in the system. Okay, you know what? I'll just start the entire solution with all of the components in it, and then I should be able to just debug through everything. But that's not going to work either, because we decided to split everything up into separate solutions. Oh yeah, and separate repositories too. Whose idea was that? Okay, I know. Let me just start up 8 different instances of Visual Studio Writer, whatever your favorite IDE is. I'll connect the necessary processes together, and then I should be able to debug through everything, right? Yeah, that should work, and I'm a very stubborn person, so I'm going at this for a while because I need to make sure that I have all the right infrastructure set up and all of that, but I got there, like a few hours fighting with this, and I'm debugging through everything. I have 157 breakpoints set all over the place. But okay, I'm looking through things, and I'm like really, really close to finding the problem. Like you have that gut feeling, you're like, I almost got it, just leave me alone for 5 more minutes. And I think to myself, okay, this breakpoint, F10, F10, I should be able to hit F5 to the next breakpoint. So I hit F5, everything pauses for a second, and I hit another breakpoint, and I'm like, dang it, I forgot another breakpoint. At that point, I have Mediterranean roots. I'm already cursing in at least 3 different languages. I need a break. It's like, okay, step outside, do some breathing exercises, maybe have some calming tea or something. And I think to myself, Laila, get it together. Like, seriously, just debugging this. How can I do this? Oh, I know. Let me add some logging. So I go back in, fresh energy, start adding some log statements all over the place. And I'm looking at that information that's being emitted, still debugging through the whole system. And I going through things, and I see order 256. And I'm like, wait a second, wasn't I just debugging order 325? Is this message even mine? So I look at my colleagues, and I'm like, is there anyone creating orders on the testing environment? Because I am debugging something now, so don't touch anything. Now, at that point, my colleagues look at me in disbelief. They're like, Laila, what are you doing? Are you debugging the whole system? You know, I'm trying to fix this issue. And they say, well, do you think anyone at Amazon runs into a failure and thinks to themselves, oh, let me just fire up the Amazon and I'll debug through this? Well, you know, if you put it like that, I guess not. But then the question is, what do we then do instead, right? Well, we test. And if I'm stating the obvious to you right now, awesome. Because testing is important independent of any architectural style that we are using in the system. But if we're running in a message-based system where components are interacting with each other all the time, then it's really crucial to have a sort of strong testing strategy to support that as well. So any testing strategies are sort of outside the scope of this talk, but I do want to give you sort of a few things to remember, especially in the context of testing message-based systems. And I have rethinking the rule of 3. What does that mean? Well, I've used for years the AAA syntax. Who's ever used that before? Okay, cool. But there's given, when, then. Who's used that before? Right, but it's all sort of the same thing, right? You're preparing some input, you execute a test scenario, and then you're going to verify what the system has done and whether that sort of matches your expectations. So if you think about that in terms of messaging, when you sort of prepare that test input, we want to prepare a message. And as part of executing that sort of action, we're going to invoke the message handler that's going to be responsible for basically processing that message. But it's a verification phase where things get a little bit more interesting. Because not only do we want to verify any desired outcome in terms of data modifications, API calls, or whatnot, but we also want to verify any of the outgoing messages that were sent or published as part of basically processing that specific message. Why is that so important? Because that's how we're doing the handoff to the next component in the system. The next component, whoever is receiving that message or subscribed to that event, is going to be making decisions based on that information that they are receiving there. So it's really important to check that, including whatever content that is in those messages. That's all good, but as always, the devil is in the details, right? And with the details, I mean the order. So one common mistake that we tend to make a lot when we write code is that we tend to make a lot of assumptions about the state that the system finds itself in. And the thing is that if those assumptions don't hold up in a production environment, then your handlers might start failing all over the place. Now, that's a little abstract, so let's take a look at an example. I have this sort of naive stock update implementation here. So this is the sort of update product stock handler, and what we are doing is I'm looking at what the message payload tells me, increase stock, decrease stock, and I'm just executing that. But we also added a guard clause, because you cannot have a negative stock. I mean, who has minus 10 PlayStations in stock? That doesn't make any sense. But the thing is that that's an assumption right there. Because is it really true that the stock can never, ever be negative? Let's walk through this for a second and sort of zoom in into how this domain is set up currently. So the way it works now, we have that place order coming in sales, we make sure it's paid, and then that becomes a sort of trigger to update the stock. But imagine that, it's release day, right, for whatever PlayStation or whatever thing you like. I'm not really a gamer, so I don't care as much. But and there's so many sales coming in at the same time. And someone is receiving a massive truck of PlayStations on the other side, goes in, puts that into the system. That's an increased stock message, right? At the same time, we're selling a massive amount of PlayStation, resulting in those decreased stocks. Now, there's all in the same queue, right? But that increased stock message, somewhere at the bottom, in the meantime, we are selling it. So we have all of the stock available. System doesn't reflect it yet. So it's situations like these that could trigger that sort of guard clause to make the system explode at that point. So you could say, well, we'll just reserve the stock immediately when you complete the sale, right? And although you might be able to sort of alleviate the problem a little bit, you're not going to get rid of it entirely. It might still happen, especially if you're running in sort of high throughput scenarios. And you might think to yourself, well, okay, we'll just reserve the stock whenever you put something in your shopping basket. That's possible. I've actually seen web shops doing this. But there's also a risk to that, right? Because I like to shop around on plenty of web shops, put a lot of stuff in my shopping basket. Does that mean I buy all of it? No, I don't think my husband would appreciate that, right? So that's also a risk. So how do we solve this type of problem then instead? Well, the thing is that we need to let go of this assumption that the stock cannot be negative, and then we can start looking at what type of scenarios that opens up. So in this scenario, we could say, whenever our order is placed, what we're going to do is basically send a message to the stock endpoint and say, hey, do you have this stock available? If stock says, yep, I have everything, cool, then everything is good in the world, right? And then we can just move on and basically complete the sale. If there's insufficient stock, then we could, for example, do something like, okay, we're going to send a delayed message 2 days in the future and basically go verify whether this sale was now completely shipped. And if not, we're going to refund that order. And this is actually a real-life scenario, because a few years ago at this point, when we were in the middle of COVID, I was sort of shopping around for a big home office screen, 49-inch, because reasons. And I was trying to find someone, and they were depleted everywhere. So I was just hoping to find one in stock. Found one shop in the Netherlands. I'm from Belgium. And it said next day delivery. So I was like, okay, let me just quickly order this. And I was happy. And then 2 hours later, I get an email in my inbox saying, sorry, it's out of stock. But we're going to back order this for you. And if it doesn't arrive to your house within 2-3 business days, then we'll just refund your money. Right? If you're looking at this example and thinking, but I have 5 other possible solutions. Sure you do. I'm sure, I believe you, and there's probably even better solutions. But what I'm trying to sort of make you think about is to start thinking about the assumptions that you have hidden in your code base. Think, what if this doesn't hold up in a production environment? What effect is that going to have on the system? And could I basically be modeling things in a different manner so that we could just not run into this problem at all and just handle it differently? So this is where we want to talk to our business experts, right? Because if you would go with this specific scenario to a business expert and say, well, we can't sell any stock that we don't have, they'll tell you, of course we can. Just sell everything. We'll try to back order or give them a voucher, and then we already have the money, and they'll just have to spend it with us. Right? That's how businesses work. So, okay, let's recap this first part. Do you run into a failure? Do you want to add more tests? You're missing at least one, but probably more test scenarios whenever you run into a failure. Right? Also, assert any outgoing messages that are being sent or published as part of processing a specific incoming message. And then also be very aware of the assumptions that you're making in the system. And one of the tools that I like to sort of use when I talk to business experts, because remember that even these people have been sort of working with you on a system for maybe years. And they also get stuck in their own assumptions. So sometimes it's helpful to say, what if there was no computer system at all? What if you were just running this as a sort of physical environment, just a shop, and running this with the books? What would you do? And that can sort of sometimes give you a completely different perspective as well. And finally, expect out-of-order messages to happen. They will happen. Don't put your hand in the sand. It could be concurrency, retries. It could be infrastructure reliability, whatever it is. We can't always assume that things are going to happen exactly in the specific order that we expect them to. So, okay, our teams, Lorem, Ipsum, and Dollar, they took this really seriously, and they came up with a very consistent testing strategy, continuous integration, everything looks green. They're like, okay, let's go to production. We're good to go. So they do that, and they've been running actually quite successfully in production for a while. But then there's this guy Murphy that comes knocking down their door, and a failure occurs in production. Well, what do we do then? Failure. We add more. Tests, thank you. Just said it, right? So whenever you run into a failure, you add more tests. But the thing is, what if you look at that message payload and you think to yourself, this doesn't make any sense. This data is bogus. Like, of course this fails. Like, how did I get this information to begin with? So let's go back to our previous example of that call stack, right? So we run into an invalid operation exception because that product does not exist. So the product ID basically doesn't make any sense. Now, in order to understand where we got that from, we need to understand where does this information come from. It basically came upstream, right? So we go up and we realize, oh, it's due to that order packaged event being published that we sent that update stock message to begin with. But that was just sort of for reaching over those order lines and taking the information that was in there. So we need to go up further and see, oh, it was when the order placed event was published that those product IDs were incorrectly mapped. Now, the thing is, how do we solve such problems in a distributed system? Well, we basically need the big picture. We can't really look at a sort of single component to be able to catch these larger problems, because clearly this is a simple example. But imagine, that happening like 10 messages upstream, and then it becomes a lot more complex. So we need to be able to sort of follow the business transaction through all of those participating components, right? That could be REST APIs, it could be other components, it could be messages flowing through a message broker, anything you're getting from the database, and so forth. And we also want to include context for sort of each of those individual steps that take part in that business transaction as well. And that's exactly what distributed tracing is for. So distributed tracing is getting like a lot of attention lately, probably due to the rise of microservices, but it's actually not that new. It sort of emerged in the late 2000s when a lot of the things that we were talking about was service-oriented architecture still, right? Now, the thing is that it doesn't really matter which type of architectural style that you are using in your system, because once you start decoupling the system and you have multiple components that are interacting with each other, you sort of need to be able to understand how those components are interacting with each other, what data is being passed along, in which order, and so forth, to be able to understand these types of problems. So, okay, our teams are like, distributed tracing. We need to do this. And if you remember, our teams operate autonomously, right? They could choose whatever tools, frameworks, and whatever it was that best suits their own needs. So they start looking at what's available out there for distributed tracing, and they see, wow, there's actually a bunch of frameworks and tools available for us to choose from. So what happens is that you have Team Lorem that says, let's use Jaeger. And then you have Team Ipsum that says, well, we're already using Azure Monitor Application Insights, so we might as well go with that one. And it's really problems like these that made them clash, because what's happening is that although each of those teams are basically collecting very useful instrumentation from their systems, the problem is that's stored in a vendor-specific format. And it's problems like these that sort of lead to a sort of higher need for standardizations. What do we then do as an industry? Create multiple standards. Right? So we have the Cloud Native Computing Foundation with their open tracing specification for distributed traces. And around the same time frame, Google open sourced their open census specification, which is a sort of standard for tracing and metrics. And then, as an industry, we're good at this, right? We always just keep creating another standard until we have 15. But this time, these teams got together and said, come on, let's get it together for once, right, and try to sort of merge them together. And that's how OpenTelemetry came to be. So they basically looked at each individual, the sort of individual strength of each specification, merged them together, provided an upgrade path for the previous users, and took that into account when working on OpenTelemetry. So what is OpenTelemetry exactly? It's basically a sort of open source observability framework composed of a set of tools, APIs, and SDKs. And the sort of goal of this project is that we can basically standardize how teams instrument, analyze, and export telemetry information from their applications. It's also available cross-platform, cross-runtime. I think at this point it's 11 programming languages or something like that. So even if you're using multiple stacks, you're probably covered. And the thing is, I'm saying observability framework. Who's heard of that word before, observability? Okay, that's actually quite a lot. But it's quite a new term, so I'm going to take some time to explain it anyway, right? Because for software to be observable, right, we need to understand the inner workings of a system, which means that we need to understand any expected state that the system may arrive to, but also any unexpected state, right? The unknown unknowns. And you need to be able to do that without changing any code, deploying new versions, adding log statements, stuff like that. That's not what observability is. The idea is that we're going to collect information inside the application, then go store that outside of the application, and then we can use specialized tools to sort of query and analyze that information in order to get actionable insights to go and improve our application. So no going into your database and querying things, that's not really what observability is, right? And OpenTelemetry supports multiple ways of increasing the observability of a system. It supports 3 so-called observability signals: traces, logs, and metrics. And each of these are sort of individual components that provide some insight into what is happening inside the application as well. But I sort of like to look at these as metrics or your sort of known unknowns, because if you're capturing a metric, then it's probably something that you expect might go wrong at some point. But you're probably going to have to rely on your traces and your logs whenever an unknown unknown is going to occur in a production environment. So let's start with traces. What is a trace exactly? Well, a trace is going to track the progression of a request across multiple components of your system. And I like to think of this as a sort of business transaction that's occurring in the system. It's basically, you could represent it as a sort of tree of spans, and a span is basically a single unit of work that is occurring as part of that distributed trace. Could be getting a message off a broker, could be querying for some data, could be just a sort of expensive calculation that is happening in the system. And each of those spans then also carries a context. So think of that as sort of key value pairs that give you a little bit more insight into what is happening in that specific unit of work, what data is being passed along, what are we making decisions based upon. That's a little bit abstract. So let's take a look at a visual representation. So as you can see on the right, that's basically the same trace ID for all of those spans. So each individual colored block is a span that is participating in that larger distributed trace. And as you can see, they're also being emitted by different components, right? So they're coming from different processes, different services altogether. And if you sort of take a step back and look at that, you might think, well, that looks kind of familiar, because it's basically a distributed call stack that we've built. And it gets even better, because what we can do is we can sort of zoom in into an individual span, right, that represents an individual unit of work that took part in that larger trace, and we can take a look at the sort of context that that carried, right? So we can see here the message ID, which destination that was being sent to, and then some information about the order as well. We can also see some events that were emitted as part of that unit of work, and that gives us a lot more insight into what was happening. So to bring it back to the previous example that I was completely unable to debug, then what we would do is we would go into our observability backend, and I'll talk a little bit about that later, and we would try to find failed spans. And then the update product stock spans would come up. And we would see, okay, those don't tell us anything, but at that point we can sort of navigate up the tree to try to understand where we can see some context that looks off. And that would then lead us to that order placed event where we can basically see that the IDs were incorrectly mapped. Now, the question is, how does this trace sort of work? How does that get connected across so many boundaries, right? Because we're crossing the network, we're crossing security boundaries. How does that work? Well, for that trace to sort of be connected, therefore distributed, we need some kind of a propagation mechanism. And that usually happens through a standardized protocol. And one of the protocols that's recognized by the OpenTelemetry project is the W3C trace context for HTTP headers. Rolls off the tongue. I don't know why they make it so incredibly long. What it really does, adds a trace parent header to every outgoing request. Looks a little bit like this, sort of concatenation of multiple IDs, but looking at the hyphens, they do have some meaning. So the first part is basically the version of the protocol, in this case 0, The second part is a trace ID. That is going to be assigned when basically the distributed trace starts, and at that point it's going to be copied by each subsequent span that participates in that distributed trace. So that next section is a span ID that's going to be unique for every span. And finally, we have some trace flags to indicate sampling decisions and things like that. So if you're in the .NET space, hands, oh, almost anyone, then you want to get started with this, and Microsoft has made it easy for you. Why? Because they built it into .NET. It's available from .NET 5 and onwards in the Activity API. Or if you're still running on previous versions of .NET, or God forbid, .NET Framework, there's still plenty of very successful .NET Framework applications running in production, so absolutely no shame in that. Then you can just pull in the system diagnostic source NuGet package to get basically access to the same capabilities. And it's pretty easy to sort of set up tracing, because the only thing you need to do is select the sources from which you want to collect instrumentation, and then set up a sort of exporter to then send that telemetry to an observability backend. And you hardly really need to change any code for that. So let me show you a snippet. If you're using the .NET generic host, it could look as simple as this. So I'm basically pulling in the OpenTelemetry extensions hosting package. That makes that add OpenTelemetry method available. And then at that point, I want to give a sort of very recognizable name to my service, because remember that that data is going to be stored outside of the application. So you want to be able to understand which specific component emitted that information. So make sure that that's not bogus, right? And then you want to collect, you basically set up the sources from which you want to collect tracing information in this example. And then you could set up exporters like this. This is the sort of easiest way to do this. What it means that each individual service that is set up this way will basically collect the information and immediately send it to the exporter. There are way more advanced scenarios to set this up with the OpenTelemetry collector, but that's for another session. I hope to be back, right? So if you're looking at the sort of exporters that you could use, or more accurately, the observability backends, there are multiple choices available, right? The beauty of a standard is that it doesn't really matter which specific observability backend that you're using, right? Because that data is going to be stored in the same format. So whatever works for you, whatever needs you have within your team, within your system, look at the right tooling and just go with that. But before you start adding any application-specific tracing, we need to start looking at what's out there, because the community really has us covered with this. There's been a lot of support for the OpenTelemetry project. It's actually the second most popular or highest velocity project after Kubernetes, so it's pretty crazy. And if you look at what type of sort of frameworks you might be using in your application, you'll find that there's already OpenTelemetry support for many of those. And if you sort of look at this, and if you think about the sort of challenges of debugging distributed systems, it's usually that we have blind spot wherever inter-service communication occurs. But if you just look at all of the packages that we have here, we're already covered, right? We have HTTP client, ASP.NET Core, gRPC. We have any messaging libraries that already have support for instrumentation that would give us sort of that insight, and then we can go in and enrich that information. Now, if you go and you start reading the documentation, the OpenTelemetry specification documentation, you look at some .NET documentation, you're going to get confused really quickly, because they basically are using different type of language. Now, why is that? Because Microsoft already had a sort of tracing API available, the Activity API. And instead of sort of creating a completely new API, what they did is basically implement the OpenTelemetry specification inside the Activity API. So there's a few things that you need to be aware of. Probably because they didn't want to rewrite half of their own applications, right? But if you see the mention of a tracer in OpenTelemetry, that's an activity source in .NET. A span is represented by an activity, span context, activity context. And finally, the span attributes are tags on the activity in .NET. If you're running in a sort of multi-stack type of system and you really want to keep the language the same, then there's also a shim available that you can use, but that requires adding in another package. Okay, so before we actually look at the code on how you sort of add tracing to your application, I want to take some time and sort of think through what is the type of information that you should be adding tracing for to begin with, right? And one of the examples that I like to use is how many times we close issues because we can't reproduce them. Who's ever closed an issue because you can't reproduce them? I want to see every hand, because otherwise you're not being honest. Or you fell asleep. We even have banners for it, right? It works on my machine. I have one on my laptop here. But imagine if you could easily connect a specific user action to a trace and say, oh, that was John, Friday, 3 p.m., and find the trace. Then we could actually go back and look at the friction that that user experienced. Because I promise you, they were not imagining it, right? The thing is that when users use a system, they're not paying attention to each individual action that they're executing and sort of looking at that order. So when something happens, they're like, what did I do? They'll just raise an issue with the information that they remember, right? But if we can just easily connect that, we can get the entire scope of information to understand what occurred. Another question to ask yourself is how easily can you sort of group similar traces together? Things that stand out in latency, in specific attributes that they carry, so that you could sort of understand what things stand out there, maybe in performance as well. Can you identify the most load-generating operations in your system? Do they happen in a specific part of your user base? Or do they happen maybe at a specific time in the day? Are they specific to a geographical location, and do you need to maybe scale out parts of your infrastructure? Can you identify which users are stressing out your system? What are they doing? And in which order are they doing things? Why do they get to sort of create that friction in the system as opposed to other users? And finally, how easily can you find suspicious events throughout the systems? Right? Is there someone doing something funky? Or another completely other example. Let's say that you wrote a bug. You're like, okay, mea culpa, I'll fix it, deploy it. And then someone from the business walks up to you and says, hey, Laila, good that you fixed the bug. Can you tell me how many customers were affected by this? I don't know. Observability could also help you sort of answer those types of questions as well. So I look at these sort of questions as seeds to plant in your brain, and I think what I would recommend is that you come up with your own set of questions and document them on what you expect to get out of the telemetry that you are collecting from your application, so that we can also do this in a sort of consistent manner and get the same quality of instrumentation across an entire system, multiple teams, multiple people working on it as well. Okay? Now we can finally look at some code. So if you want to start creating some application-specific traces in .NET, you're going to need an activity source. Now, that needs to be uniquely named, representing the component that's submitting the telemetry. And you could ask yourself whether you want to use subcomponents or use some kind of configuration. Now, think about the amount of traces that you're emitting. Right? If there are any traces that you want to be able to opt out from, so you want less sort of spans to be collected as part of that distributed trace, then what you would do is create an additional activity source. And you could maybe end up with stock.core and stock.calculation. Whoever wants the telemetry from both can just add source stock.star, and you get the both. If, on the other hand, you're looking at, no, I want all of the spans, but I want to be able to sort of opt out from specific attributes, for example, that are being collected, then you're more looking at configuration. I'll give you an example. If you add, for example, add SQL client instrumentation, then you have a configuration method available to say, I want to capture the database statements, or I don't. Right? So that's an example of configuration. And then basically you can create this once as a static and share it inside your components, totally fine. Now, OpenTelemetry also works based on a sort of opt-in model. So it's not because you're creating all of these traces and that instrumentation that it's also actually being collected. You still need to opt in. How do we do that? By adding the source, right? We say add source stock in this specific example, and it's really important that those string literals are also going to match. When it comes to the sort of code that we want to instrument and add some insight to, what I'm doing here is I'm using that activity source that I instantiated earlier, and I'm creating an activity based on that source. Now, that gives me a nullable activity. That's basically a performance optimization, because like I said earlier, the way that this API is implemented is an opt-in model, which means that if nobody is listening, I'm getting a null reference. So be careful and make sure to add that question mark. I'm making use of the using statement, not only because I want to dispose of everything correctly, but also because this will call stop activity for me. So I don't need to remember to do that and stop the span exactly where you want it to be stopped. And then you can add some tags in this case, or attributes in the OpenTelemetry spec naming. And that would be like, if you look at a piece of code, right, ask yourself, if I would be debugging this, what would be of interest to me? Like, what are the parameters that stand out that could be impacting the decisions that are being made within this piece of code? And that's something that you want to consider adding in there. You can also add some events. By the way, this is a terrible example, which gives me an opportunity to talk about that, because if you were actually recalculating the stock, you'd create a dedicated span. So you can also see how long does that take and all of that, right? But you could have whatever sort of logging type of comment you would add to events. And then I'm also catching any exception that might occur. Why? Because I want to set specific tags on that span or activity to sort of signal to the observability backend that this went wrong. This is also the perfect place to sort of capture additional tags in case you want some extra insight that you don't want to capture when everything goes right, but you only want to capture that when things go wrong, okay? Don't forget the rethrow. Now, I also want to sort of quickly circle back to that version right there, because I skipped it earlier, not because I don't care, but because I thought it deserved its own slide. Now, why is that important? Because as our code evolves, so does the instrumentation that it emits, right? So it's important to make those versioning changes explicit in your observability backend, because that will also be visible when you are querying that information. Remember that that information is stored outside of the application, right? And it might be really interesting when sort of trying to understand specific things that you're observing in that data to understand which version of that component that information came from. So, okay, our teams are doing this. They're like, you know, this is really, really helpful. And they start looking at this code and they wonder, like, this looks a lot like logging. So then the question rises of, should we stop logging altogether and just focus on distributed tracing instead? And this is sort of a complicated question. It's like the typical it depends answer, right? Because if you compare logs to traces, tracing really has the sort of richest data model as opposed to logs, because you can add attributes, you can sort of connect those across multiple components, which is usually a very big pain if you want to do that sort of log correlation across multiple components. But on the other hand, the OpenTelemetry project is also working really hard on making that sort of cross-component log correlation a lot better, I guess. So yeah, what I would say is, if you are free to choose, and if it fits within the team that you're working with, then yes, prefer those distributed traces, especially in a distributed environment, right? But the thing is that we have been logging for years in our applications, right? And there's no need to go back to your manager and say, okay, I watched this talk at NDC Oslo, can you please give me 2 months because I need to replace all of our logs with traces? No. Don't do that, right? You can sort of gradually sort of go and start using traces where it makes sense. And then what is really, really important is that we sort of connect the traces and the logs that we already have in our system, connect those together through sort of cross-signal correlation. And again, if you're running in the sort of Microsoft stack, super easy if you're using the Microsoft Extensions logging framework, because we can basically add OpenTelemetry, and what this is going to do is apply the OpenTelemetry sort of logging format to any log statement that is going to be emitted from your application. And then I'm also setting up some exporters so that I can collect that information, again, in one of those observability backends. Now, what is the result of doing something like this? It looks a little bit like this. And the most important part, in my opinion, is that it adds that trace ID and that span ID to every log statement that is being emitted. That means that it doesn't matter what you're looking at. If you're looking at your logs, you have the active span ID and the trace ID available. You can go into whatever observability backend that you're using for your traces and go query for that. And the other way around as well. If you're looking at the traces, you can find all of the correlated logs as well. And that makes it really powerful to have that sort of cross-signal observability in your system. So what about metrics? Because I've talked about traces and I've talked about logs, but I haven't really talked about metrics a lot. Well, it's sort of a signal on its own, right? I do want to drop a few sort of pointers, but basically they're scalar values accumulated over time to sort of represent a specific state of the system. It could be message throughput, right? And messaging is something that we really like to look at. But it could also be the failure rate, right? Which then makes a very good base for alerts. So if we have more than, 10 failures in a span of a few minutes, then I want someone to be woken up. PagerDuty alerts everywhere. Could be something that you want to do, or emails, or whatever it is. Right? So it's really good to sort of do proactive monitoring. Now, the thing is with metrics is that you're only going to monitor things that you can already expect to go wrong. And it's really an indication of a problem, but it doesn't give you a lot of insight into what's going on. Now, there are things that we can do to sort of improve that, and that is by doing metric correlation, so that we would capture what is called in OpenTelemetry metric exemplars, to basically add some information to the metric that we are collecting, so that we would then be able to connect that to the traces and the logs that were emitted and that sort of fed into that metric looking a little bit out of whack. Okay, so I've told you all of these glorious things about OpenTelemetry and observability. And you might be thinking, what's the catch? And I mean, there's multiple ones. Because first of all, there's going to be some memory overhead in your applications. Now, you need to be running at a massive scale if this is what you care about, right? In any sort of regular application, this is not something that you're probably going to have to be concerned about, because these APIs were basically also created with performance optimization in mind. But if you're running at a massive scale, there's going to be some memory overhead. There's also going to be some added latency and some additional bandwidth that you're using, right? Because some information is being propagated across services, so you're adding some headers here and there. And then you're also using additional bandwidth to send that information to the observability backend as well. There's also going to be a storage cost, because we have to store that data somewhere, and usually that's not free. And we're also introducing new tools. Some of those might require a license. We also have to educate our team, not only to start, creating traces and logs and metrics inside the application, that's one end, but also then using those tools, to sort of query those observability backends and look at the information that we have available to sort of extract actionable insights that can help us go and improve our applications. And then finally, there's maintenance. Because any type of code that we add to our systems is going to evolve, whether that's production code or testing code, or in this case, instrumentation code, right? Every letter of code is an added cost, and it's going to have to be maintained by teams that are also changing over time. And it's a thing to consider. As you can see, I started cheap, and then it became more expensive. Now, that doesn't mean that you shouldn't be adding observability to a system, right? I just spent an hour telling you that you should. But I just want to make you aware that with whatever decision we make, whatever architectural style, whatever tools you introduce, there's always a trade-off that you are making. So it's important to be aware of those as well. Okay, so if you decide to do this and you're creating additional observability in the system, you get additional benefits, because what I've been talking about for almost a full hour at this point is really failure investigation, right? So how are we able to sort of understand the root cause of problems in a larger systems where components are communicating with each other over messages or whatever other communication pattern that you might be using. But there are plenty of other benefits that you could get. First of all, observability could be a driver to basically understand where your system is slow, where you see higher latency. How many times does someone walk up to you and say, the system is slow? And you're like, okay, what is slow? Where is it slow? What were you doing, right? But if we have added observability in the system, it would be easier for us to sort of go query and understand where that latency is. When does it happen? Because usually if we're running in a development and a testing environment, everything is speed of light all the time. And then in a production environment, things change, and it's like, okay, what's going on? It also gives you sort of the ability to perform postmortems. Yeah, a really dark word, but think of a sort of Black Friday, Cyber Monday, right? Everything went kind of okay. System didn't completely come crashing down, thank God. But we also want to go back and reflect and say, okay, how did this go? Can we further improve this for next time? Right? Maybe if we're running in the cloud, we have configurations that allow us to auto-scale our services. So was that configuration good? Did we scale up quickly enough? Or maybe even more importantly, did we scale back down quickly enough so that we don't have those massive bills? Right? So this can also give you that insight. Another sort of possible benefit is feature flagging. Let's say that you have a very large system and you're adding a feature to that system and you don't want to go and release it to the entire user base. First of all, you want to release it to a sort of segment of that user base and then start to see, is this even being used? And when it's used, do any exceptions pop up? Are there any issues with that? Does it have a sort of performance or latency impact on the rest of the system so that we can sort of understand how that's doing before we go and release it to the entire user base? Finally, we also have chaos engineering, right? Who's heard of chaos engineering before? Okay, plenty of hands. Well, we now have sort of services available like Azure Chaos Studio, Chaos Monkey, and those sort of allow us to sort of unleash chaos on the system, push it to its limits, and see where it starts breaking first. That's a sort of really good strategy to increase the resilience of a system and see how it could better sort of support our production environments. But if you use a service like that, and you see a bunch of errors, and you have zero observability in your system, then how are you going to figure out what went wrong and what needs to be improved in order to not be in that same situation when that chaos is caused by your users in a production environment? Because without observability, you're going to be looking for lots of needles in many, 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 many haystacks, right? So, okay, we've sort of reached the end of the session, so we can slowly recap. Specifically when thinking about failure investigation, solving issues in a sort of production environment, I like to think of observability as a way to replace the call stack that we gave up when we sort of transitioned from a sort of monolithic architecture to a more distributed architecture where there are multiple components interacting with each other. Does that mean that you're never going to have to debug again? Nope. But hopefully it will not be as painful as what I sort of portrayed in the beginning of this session, right? So we'll add more tests. We'll be able to do that zoom out, zoom in based on our distributed tracing, understand where things are going wrong, add tests there, and maybe that will require some debugging here and there. So it will be localized and hopefully pain-free. If you're ready to get started, like I said, there's no need to go back to your manager and say, I need 3 months now. No, we can just start by investigating the instrumentation libraries that are available out there for the frameworks that you're already using in your application, because you will see that those already provide a lot of visibility into what's happening with the system. Even those spans that are being emitted can be accessed through activity.current, and you can then go and add some additional tags to those activities to sort of further enrich them, even without adding any application-specific spans. And then connect all of that information to your logs, right? One of the, in my opinion at least, one of the sort of advantages of the OpenTelemetry project is their focus on signal correlation, cross-signal correlation. So we have metrics, logs, and traces. But being able to connect all of that information together is really going to give us the maximum amount of value of that observability in our system. And then slowly enhance and enrich from there, right? Take it slowly, gradual improvements until you get to the point that is sufficiently observable for your system to be running successfully in production. Okay, that was it. If you have any questions, I'm happy to hear them. Feel free to scan the QR code. It will take you to one of my GitHub repositories. I have additional resources there available for you. Also a sample that you can run based on in-service bus. If you have any questions, feel free to come and ask me. And you can also find me for the rest of the day at a particular software booth as well. Thank you for listening.